very good afternoon to Dr. Husni Mokhtar, our project director Mohamad and my fellow committee members. And of course, we can't forget everyone else in WebEx and YouTube. I'm Leong Yesian, and I'll be the MC for today. As was publicized, today's session will be centered around Introduction to Quantum Gravity by Dr. Husni. Before we begin, let us invite our project director Afiq to give a welcoming speech before reciting the prayers.
Bismillahirrahmanirrahim. Thank you to our MC, Leong. I am delighted and deeply appreciate all the people who have attended our program today. I hope that and every one of you will gain knowledge and goodness from this program. Perhaps there are some the participants who are not familiar with the concept of quantum gravity. So this program aims to provide additional knowledge to all happy learning. Now we will proceed to the prayer. Bismillahirrahmanirrahim. Alhamdulillahi Rabbil Alamin. Wassalatu wassalamu ala ashrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Ya Allah, on this afternoon, in connection with the program of introduction to quantum gravity, we be safety and grateful towards you in favor of all the infinite blessing to us, your humble servant, to live in safe and prosperous life. We seek your blessing for a flawless progress of this event from the beginning until the end. We seek your guidance to stay clear of event that will determine the progress of this event. Ya Latif Ya Rahman, please bless us with your tawfiq and hidayah. Please guide us to greatness, peace, glory, and prosperity in this world and the hereafter. Make us responsible intellectual. ربنا هاتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار وصلى الله على نبينا محمد وعلى آله وصحبه أجمعين والحمد لله رب العالمين. Now I pass to Leong.
Project Director Afiq. Moving on, we will pass the stage to Dr. Husni to start the sharing session. For your information, Dr. Husni is a theoretical physicist specialized in quantum gravity and quantum field theory in curved spacetime. He has completed his bachelor's degree at the University of Manchester, his master's degree in quantum fields and fundamental forces at Imperial College London, and finally his PhD in mathematics in the University of Nottingham. If any participants have any questions during the talk, kindly note it down as we'll be having a Q&A session after the talk. Now, please welcome Dr. Husni.
Hello, Assalamualaikum everyone. Can you hear me clearly? Can I get some feedback? Okay, good. Okay. So yeah, wait a second. Let me share my screen first and then we'll start. All right. Okay. So hopefully you can see my screen now, right? Okay. Thank you. Just open the chat box for a while. All right. Okay. Okay. Thank you everyone for joining this talk. So for start, so to begin this talk, let me begin by thanking the organizers, Persatuan Sains Fizik of USM, for inviting me to give this talk over here, to give this talk about the introduction to quantum gravity. So before I start, let me just say that so this topic is still quite a vast topic. Okay, so there are various approaches to quantum gravity, but hopefully, even if I'm not going to be able to go into the details of all the various approaches, hopefully I will still be able to give you an overview about quantum gravity as a whole, as well as an overview about some of the approaches that we try towards achieving a quantum gravity, or towards having a quantum theory of gravity. Okay, now to begin with, let me start with something that we all know. Okay. Oh yeah. Before that, throughout my talk, I will be using all of these acronyms over here throughout my slides, because I will not keep on writing quantum gravity, quantum mechanics, quantum field theory, etc. Instead, I will just use these acronyms over here. In particular, QG is going to stand for quantum gravity. GR is going to stand for general relativity. All right. And the rest, for example, QM stands for quantum mechanics, etc. Okay, now to begin my talk, let me begin with things that we are all familiar with. All right. Now, when we observe the world around us, we can observe that there are various phenomena. We can observe that there are various phenomena around us. Right. We can see, for example, from the motion of rigid objects, from the flow of water as shown over here, to the shining of the sun over here, right? And when observing all of these phenomena, I think I can safely say that physics is about us trying. At least one of the aim of physics is about us trying to provide an explanation to all of these phenomena. All right, and in doing so, there are various levels in which we can explain all of these phenomena. Take, for example, about this flowing of water over here, right? We can use, for example, fluid mechanics using concepts like buoyancy, laminar flow, turbulent flow, etc., to explain the flow of water. Okay, and then so that kind of explanation is what we call as the explanation or description at the macroscopic level. All right. And then from there, we can dig deeper and find out that the water is made up of water molecules. All right. And from that, and then from then on, we can then go on to describe this phenomena of flowing water from the perspective of those water molecules. Right. We can use a more fundamental concepts, like for example, Newton's first law, etc., Newton's first law, second law, etc., in order to explain the phenomena. Okay. Now, uh, uh, as far as we know, right? As far as we know, to the best of our knowledge at the moment, it seems like at the most fundamental level, um, our world is best described by these two distinct theories or frameworks. All right. On one hand, we have quantum mechanics or quantum field theory, right, which describes everything in the universe at the fundamental level. Okay. We can use this theory, this quantum field theory, to describe matter as well as non-gravitational interaction. Okay, so this quantum field theory or quantum mechanics is what underlies what is known as the standard model of elementary particles. All right, that's shown on the right over here. So what is shown on the right over here is what is the standard model that says that everything in the universe can eventually be described by these elementary particles. Okay, so even though in this diagram we can see that they show only 17 particles, in actuality we have around 61 particles. All right, because for each of these particles, for example, we have an antiparticle. Okay, and for each of these so-called quarks, we have 3 flavors. Okay, so in total we actually have around 61 elementary particles to describe our world. Okay, so that is the first theory that we use to describe the world around us. Now, the second theory that we need in order to describe our world is what it is general relativity, right? Which is the theory that we use to describe the remaining interaction, that is gravity. Okay, and together with it, we also need GR to describe the space-time itself. All right, that is what we can think of as the stage on which everything else occur. Okay, so that is what space-time is. Okay, Right. So this one is just this slide just showing you the interaction between the particles. Right. We have that the quarks interacts with bosons with the weak bosons as well as the gluons as well as the photons, and the leptons, which include the electron in particular, interacts with photon, which is the particles of light. Okay. The weak bosons. All right, but it doesn't interact with gluons, right? So gluons are the particles that is responsible for holding the quarks together to form protons as well as neutron. Okay. Okay, so this one is already established, right? And the standard model of particle physics. Okay, so the other one that is established is GR, all right, which is illustrated over here. Okay, so this picture over here, it nicely illustrates the essence of what GR is, of what what GR is. So this blue gridded region over here represent the space-times, okay, the space-time, okay, and then when we have something massive in the space-time, what it does is that that massive object is going to cause the space-time around it to curve, right? To curve, right? As illustrated by the grid lines over here. Okay, right. What that curvature does is that it causes deflection, right? It causes deflection of the path of moving objects. All right. So let me go to the next slide, which illustrate this even better. Okay. For example, let's have a look at this left picture first. All right. So suppose that we are observing two stars from the Earth. Okay. So these two white things over here are stars. All right. At their respective actual position. Okay. In the absence of anything between us and the stars, the light from the star is just going to travel in straight line to Earth, right? To us, okay, on the Earth, okay. And then supposing that we have, and then later suppose that we have something that is the sun that is between the star and us on the Earth. All right. So what this sun does is that this sun uh, causes the space-time around it to curve, and what that does is that it causes the path of light from the star to be deflected. All right. As it reaches us, it is deflected. Okay. But for us, we would still perceive as if the light traveled in a straight line. Okay. As a result, we are going to perceive the distance of the star, as shown in this diagram over here, to be at this point and at this point. Okay, so as a result, in the presence of a massive object, all right, we are going to perceive the position of the star at a slightly different position compared to the situation when we don't have anything that is curving the space-time around it. All right. Okay, so this one is just to illustrate to you what our current theory is. Okay, this one is just another picture that is illustrating the gravitational wave. As two massive objects are rotating around each other, that would cause disturbances in the space-time itself, in the empty space-time, and that disturbances are what we detect as the gravitational wave. All right. So this gravitational wave has been predicted since 1916 by Einstein himself, but we have only detected it very recently. Okay. So nowadays we are in a new region of astronomical observation where we can now detect. We now our technology is now advanced enough to detect gravitational wave, and hopefully this will open up a lot of new observations that could perhaps contribute to what we're going to which would perhaps contribute to quantum gravity, right? So which is the topic of our talk today. Okay, So now, having reviewed the current physics, so now let me start talking about quantum gravity. And I wanted to start by answering this question about what is quantum gravity about. Okay, what is quantum gravity about? Now, so before that, okay, now just because we have two different framework, all right, just because we have two distinct framework, in order for us to describe the universe, that alone is not a problem per se, all right, because it is not a problem for us to use different framework to describe different set of phenomena. Okay, so that one first. Even though, of course, it would be nice if we just have a single theory to describe everything. Okay, but a priori, that is not really a problem. Okay, however, yeah, and indeed, as far as we know, each of those theory, the standard model and GR, they are both very, very successful within their own realm of applicability, right? Within their own skills at which they are applicable, they are very, very successful already. All right. But then the problem is when we need both theories and we find that if we incorporate both theories in order to explain this phenomenon that require both theories, we find that it is either unclear what will actually happen or we get inconsistencies. So this is where things start to become problem. All right. This is where the fact that we have two different framework becomes a problem. Okay. Because now we are not quite sure what will actually happen, right, to that particular phenomenon. We don't really know how to describe the phenomenon, right? Simply because one theory is not sufficient to describe that phenomenon. So later we will have a look at what are some of these phenomena that requires both quantum mechanics as well as gravity in order for us to explain them. Okay, now let me go to answer this question about what quantum gravity is about. All right. Broadly speaking, research in quantum gravity, we can define it as any attempts to construct a theoretical schemes in which we use ideas from both general relativity as well as quantum theory. Okay, so this one is taken from Isham 1993, and this is a very broad definition. All right. So with this definition, for as long as you are calculating things and using principles and ideas from both GR and quantum theory, that would qualify as quantum gravity. Okay. So this means that if we use this broad definition, both quantum field theory in curved spacetime as well as what is known as semi-classical gravity qualify as quantum gravity. All right. So in both of these field, quantum field theory in curved spacetime and semi-classical gravity, in both of these, we still treat gravity using GR. We still treat gravity as a classical field, as a classical entity. Okay, but we then also treat particles and matter using quantum mechanics, which means that for the gravitational sector we use GR, whereas for the matter sector we use quantum field theory. Okay, so this one is one way to define what quantum gravity is about. Okay, but then typically when we talk about quantum gravity, typically people refer to a narrower aspect, right? That is, research in quantum gravity refers to any attempts that seeks to describe the gravitational interactions quantum mechanically, which means that we want to find what are the quantum properties of gravity itself. Okay, with this definition, both of this field that I mentioned just now would not be included as being quantum gravity. Okay, yeah, and so the purpose of this of quantum gravity with this narrower definition would be either to identify quantum properties and quantum dynamics of gravity, or to identify what are the entity from which we can derive gravity, from which we can derive classical gravity. All right. So this one I will talk a bit later. That the fact that we expect that quantum gravity effects would be significant at the Planck scale. Okay. All right. So this is the introduction. Now, for the rest of this talk, I am going to talk about the motivation for us to do quantum gravity, as well as the approaches to quantum gravity. Right. So once I've covered both of these, then I will just do some closing remarks, and then we go to Q&A session. Okay. All right. So for the motivations, I think I can summarize that there are four main motivations for us to pursue in quantum gravity. One is about unification. Second is a problem with quantum superposition, and the third and the fourth one is because we want to try to describe the early universe as well as black holes, right? So the last two are the are the two main motivations if we are to have a complete description of the universe. All right, because we believe that the universe has a beginning, the Big Bang. All right, as well as in our universe we have entities that we know as black holes, that we identify as black holes. All right, and in those black holes there will be a region where we need both quantum mechanics as well as gravity in order to properly describe those situations. Okay, now let me begin with the first motivation, which is unification. Now, as I said just now, it's not really a problem per se if we have two different frameworks to describe different phenomena in our universe, right? For as long as we can, for as long as either we need only one of them to describe the phenomenon, or if we can use both theories in a coherent way. All right. Of course, the problem is that GR and quantum mechanics doesn't play along, which means that whenever we need both, it doesn't work. All right. So there will be problems whenever we need both. But otherwise, a priori, it is still okay, right, for us to have two different theories. Having said that, however, if you look at the history of physics, you would notice that unification is somewhat of a recurring theme in physics, right? For example, we have that Newton unified the force that is responsible on Earth, all right, for the fall of an apple towards the Earth, as well as the force that is responsible for the planetary motion, and that gives us Newton's law of universal gravitation. Okay, and then later after that, we also have Maxwell that who have unified electricity and magnetism to become electromagnetism. Okay, and then we also have Einstein unified space and time to become space-time, as well as energy and also mass, right, via that E equals to mc squared, and we obtain special relativity. And then after that, Einstein also unified space-time and gravity to get general relativity. Okay, and then the most recent one, I suppose, we have this contribution by Glashow, Salam, and also Weinberg, who have unified electromagnetism and the weak force to become a single electroweak force. Okay, so we can see that there is a recurring theme of unification in physics. Okay, so because of this, it is natural for physicists to strive towards combining theories into just a single theory, or at least into a single framework. Okay, the reason why I said a single framework is that when you look at the standard model of particle physics, right, the standard model of particles, okay, what it does really is that it unifies all non-gravitational physics to describe them using a single framework, that is quantum field theory. However, the standard model of particle physics does not yet unify the three forces into a single one, right? Within the standard model, we have two distinct forces. Okay, that is the electroweak force as well as the strong force. The strong force is described by quantum chromodynamics, and the electroweak force is described by that Glacier, Salam, and Weinberg theory. Okay, but they are both described within the same quantum field theory framework. Right, we can use the same framework to describe the theory. Okay, if from there you want to go to the next level, that is, you want to describe the two forces, or should I say the three forces, into a single theory, right? That is, if you want to describe the weak force, the electromagnetic force, as well as the strong force as a single entity, as a single force, that is where you start working on what is known as the grand unified theory. All right, which is something that we also expect once if we reach to a high enough energy. Okay, and of course, if you want to go to the next level, you get the theory of everything, where you unify all the four supposedly fundamental interaction. Okay. Okay, so yeah, so this one is also showing the unification in physics. All right. Okay. So yeah. Because of this, because all of this, development in the history of physics, you can see why it is somewhat natural for physicists to just want to unify all the forces, right? Which means that in this case, we want to unify gravity with quantum. Okay. So that is one motivation. Now the second motivation that I wanted to talk about is about the quantum superposition just now. Okay, and before I talk about that one, I think it is good that I first remind all of you, or review what are the properties that we are interested in. Okay, and here I want to start by reviewing the properties of quantum objects. Okay, so the main thing that quantum theory says is that all quantum objects possess both the wave and the particle properties. All right. For example, and this is perhaps best described by this double slit experiment over here. All right, where we do experiment. Let me just say that this experiment has actually been demonstrated up to relatively large particles, right? Up to 2,000 atoms. Okay. Now back to this experiment. What we do is that we fire electrons one at a time through this double slit. Okay, through this double slit, and what we find is that, of course, as we fire the electrons, we will just see one dot at a time. Okay, one dot at a time. I think I'm going to just go to this one. Okay, so as we fire the electrons, we will only see just one dot at a time. But then, as we fire a lot of electrons, we can see that there is a pattern that emerges that is known as the interference pattern. That is characteristic of a wave. Okay, so because of this, on one hand, we have the particle properties because we detect only one dot at a time. That is particle properties. On the other hand, we also get this interference pattern, which is a pattern that is not possible if electron is just a classical particle. It's just an ordinary particle, which means that whenever we describe an electron or any quantum objects, on one hand we have some particle properties. On the other hand, we also have some wave properties. Okay, whether we want to view the wave itself as the particle or not, that I think there is some debate about that. There is some interpretation about that one. So so that one I think I'll just leave it to your preference. But the point is in order for you to describe quantum objects, you need to use both wave as well as particles, right? So this is what is known as the wave particle duality. Okay. Now, from this interference pattern, we can deduce something. We can deduce that the quantum objects must also be in a state that we call as superposition state. All right, that is, I would say that it is not actually easily describable in classical terms, because if you want to continue to use classical terms, you are going to arrive at a sort of weird description. All right, like for example, in this double slit experiment over here, okay, the fact that we see uh, these interference patterns means that uh, means that uh, means that as the individual electron passes through this slit, it has to interact with itself. Okay, it has to somehow interfere with itself. Or in other words, all right, if let's say this L over here is the state corresponding to the electron going through only the left slit, and this R over here is the state where the electron going through just the right slit. All right. In order for us to see the interference pattern, all right, uh, uh, along along the way as the electron is fired from the electron gun to arrive at the screen at the back, it must be in this state over here, right? Which is a sum of both of these states, right? So if we are to describe this state in the classical term, we would say that the electron must travel both slits at the same time, even though there is only just a single particle. Okay, so which is why I said that quantum position, quantum superposition, it is a state that if you are to use classical terms, you are going to arrive at this kind of description, right? So, so the particles being in two states at one time, even though in quantum mechanical sense, this is just a single state. It's not a many state. Okay. Okay. Now, all right. Okay. So, this one is another properties of quantum objects that is going to cause problem with quantum gravity. That is going to lead to the need of quantum gravity later. And typically, this weird superposition properties is typically illustrated using this Schrodinger's cat thought experiment. Okay, where we imagine that suppose that we have a box with a cat inside that box, right? And then we also have a flask of poison over here, all right? And we have some radioactive source. We have some radioactive source, and then this radioactive source is connected to this machine over here, which would break this flask of poison and release the poison if the particle in this radiative source has decay. Okay. Now, according to quantum mechanics, unless we at least in the standard Copenhagen interpretation, okay, unless we observe what is happening to the radioactive source, right? The radioactive source will be in a superposition state of decay plus not decay. Okay, and so because of that, because we have not observed what is happening in this box, in this box containing this cat over here, if the radioactive source is in a position of decay and not decay, then this flask is going to be in a position of intact and broken. All right, and that means that this cat is going to be in a position of alive and dead at the same time. So that is a weird thing for us to think about in classical terms, right? So of course, so far no one has ever done this thought experiment, and I hope that no one actually did it involving cats. Okay. So the point is, this thought experiment is to convey the weirdness of this quantum superposition. Okay. Okay. Now let's leave quantum things for a while and let's move on to gravity. So just a quick reminder. All right. Okay. So the part that is everyone is familiar with is this part over here, I'm sure. According to Newton's law, it says that two objects are attracted to each other according to this law over here, right? According to this law over here, and they are attracted to each other by this gravitational force. Okay. Now there is a problem with this original form of Newton's law of gravity, because it involves action at a distance. So in order to avoid that problem, we can introduce the idea of a gravitational field. All right. So the idea is the following. For any massive object, all right, for any massive object, let's say M1 over here, it is going to generate a gravitational field of this magnitude to its surrounding, right? Like for example, over here, I have illustrated that this mass generate this gravitational field, all right, at this stage. Then what this gravitational field does is that if we are to put a second mass M2, all right, the gravitational field is going to cause the force, is going to cause that gravitational force of this magnitude. All right. So in this picture, it is not really this mass. It is not really this mass that directly causes this force. All right. So this mass generates this field. So this field, this gravitational field, causes this gravitational force. Okay. So it is just a small difference, but it makes a huge impact to the conceptualities to the concept of uh, of 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 locality. Okay. 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 So then, of course, we can go on further to describe to derive the Gauss's law for gravity and to introduce the gravitational potential, etc., etc. I don't want to talk about this one, but what I want to talk is about the next one. Okay, suppose now we want to combine the situation, right? Suppose that L is a state where the mass M1 is at the left, right? Then it is clear that the gravitational field at this point is going to be pointing in this direction. Okay, and similarly, if the system is in the state R, that is the mass is on the right, then the gravitational field at this point is going to be pointing to the right. Okay. Now the problem is what happens if let's say the mass is in a superposition state of being at this point on the left as well as on the right. So what's going to happen to the gravitational field? Okay, this is a problem, you see, because GR doesn't know anything about quantum, right? In general relativity, there is no such thing as superposition state, right? There is only either on the right or on the left. Okay, so we cannot use GR to determine what's going to happen in this situation. Okay. On the other hand, quantum field theory quantum field theory or quantum mechanics or the standard model doesn't know anything about gravity. Okay. And just because of that, yeah, we cannot use the standard model to describe what is happening over here. Okay. So yeah, so supposing that we imagine this situation, which in principle could happen, right? Which if you believe in this experiment, if you believe that the electrons do travel through both slits at the same time, then there must be a tiny influence to the gravitational field. Okay, and so yeah, so the question is, what really happened in this situation? So in order for us to properly describe what's going to happen in this situation, we need both quantum as well as gravity, and hence we need quantum gravity in order to properly describe this kind of situation. Right? Perhaps gravity is just going to take the average of the two and just behave as if the mass is at the middle. Who knows, right? Yeah, until we have until you give a theory to describe what is happening over here, and you do experiment to verify this, we're never going to know. All right. Now, one of the problem in quantum gravity is the fact that it's because gravity is very weak, right? So at the microscopic level, gravity almost play no role. All right. So to see this, we can consider, for example, two electrons that is 1 meter apart, right? And then we can calculate the mutual electrostatic repulsion, and we find that the force is of the order 10 to the minus 28, which is, yeah, quite small already. Okay. But then if you go on to calculate the mutual gravitational attraction, it is even smaller than that. It's only 10 to the minus 71 Newton. All right. Which means that the electrostatic force is of the order of magnitude is of 42 orders of magnitude stronger than gravitational force. And so one of the challenges really in quantum gravity is how you want to measure these very weak forces. That is one of the major challenges in quantum gravity. Okay. All right. But then again, we are progressing, and recently we have and recently there is a breakthrough where some scientists managed to measure the gravity from just a few milligram masses, right? And this is a breakthrough because this means that we are one step closer towards measuring these very tiny forces. Okay, and this is important because if we are to design experiments that even indirect that is relevant to quantum gravity, chances are we are going to need to be able to measure very small gravitational forces, right? And so yeah, we are moving in a direction that could open up a tabletop experiment involving quantum gravity. Okay, yeah, and then of course, because in GR, gravity is not only a force in space-time, but it is the space-time itself. This means that we can ask the question of, do we have, for example, superposition of space-time? And what does it mean? All right, what does it mean? Okay, and GR make it worse because according to Newton, only massive objects would cause gravity, right? But then according to Newton, everything that has energy, according to Einstein, everything that has energy would induce curvature in the space-time. Okay, so including gravity itself. Okay, including gravity itself. All right, so this one just now I said about the Planck scale. So the Planck scale is the scale at which we expect quantum gravity effects to become significant. All right, and we can so if we look at our theory, for each our theory, there is a certain constant that is the characteristic of that theory. For example, Gravity is characterized by the gravitational constant, capital G. Quantum mechanics is characterized by the Planck's constant, h bar. And special relativity is characterized by the speed of light, c. Right? Now, using only these three constants, we can come up with all of this scale over here. All right? The scale at which we expect quantum gravity effect to become significant. Why? Because we use all three constants in order to come up with this scale. Right. So what I want to highlight in particular is this energy scale over here, which is 10 to the 18 GeV. Okay. The Large Hadron Collider, which is our largest particle colliders, can only achieve up to 13 tera electrovolt, right? Which is only just of the order of 10 to the 4 GeV. So we are still 14 orders of magnitude far from the Planck energy, which is why we don't really expect that we will be able to probe quantum gravity directly. Even though we need quantum gravity to explain certain phenomena, it's quite difficult to see how we can probe it directly. At best, we can try to design an experiment to probe quantum gravity effects indirectly. Okay. How does the time? Oh, it's already 2:45. All right. So yeah. So okay. So I've talked about two of the motivations why we need quantum gravity, right? So this just listing the importance of quantum gravity, and the other two motivation is because we want to understand the origin of the universe. All right, we want to understand the Big Bang, as well as we want to understand the final state of a black hole evaporation. Okay, so I'm just going to talk briefly about both of these. Now, the early universe. In 1929, all right, Edwin Hubble published an observation that shows that galaxies are receding further. That shows that galaxies that are further from the Earth are receding faster. Okay, and what this suggests is that it gives support to the model where the universe is expanding, right? Where the universe is not static, but instead the universe is expanding. Okay. Now, if the universe is currently expanding, all right, we can try to reverse the flow of time in our analysis. Okay. And then if the universe is currently expanding, then that means that sometime in the past, right? Sometime in the past, the universe must have been once packed in a very small, very hot, very dense region, right? That is the point that we call as the Big Bang. Okay. Now, if you look at this description over here, we have in particular very small, which means that we need quantum mechanics. All right. On the other hand, we have a very dense region, right? Which means that we are going to have a very high energy at that point. So with high energy, we're going to have a high curvature, high space-time curvature, high gravity. Okay, and hence, in order for us to properly describe this initial region of the space-time, this early universe, this very, very early universe, we are going to need both quantum mechanics as well as gravity to describe it. All right, and hence we need quantum gravity. Okay. Okay, so this one is just showing the observation from Hubble. So this one is just showing an illustration of our expanding universe where we are currently over here, right? If we reverse back in time, okay, we are going to have a time where the universe is very small, very dense. Okay, this point here. So the point at which we call as the Big Bang, right? This is just another illustration of the Big Bang theory. Okay, now, and so because of that, as I said, because of this, well, we need quantum gravity to properly describe the Big Bang, right? So far, the Big Bang originates from GR, all right. But for your information, as far as GR is concerned, the Big Bang is a point of singularity, right? It is a point of singularity that is precisely the point where GR would no longer be applicable, all right? Because GR breaks down at that point of singularity. So yeah, so even though GR comes from, even though Big Bang comes from GR, GR itself is not capable of describing what the Big Bang is. Okay. Okay, so this one is the next motivation. So the last motivation comes from the black hole. All right. So a black hole, just to remind you, so a black hole is just a region of space-time in which the gravitational force is so strong that nothing can escape from it. All right, and it can form from a star that has collapsed under its own gravity. All right, and from analysis, we expect that this would happen. A black hole would form when a star with a mass of larger than 3 solar mass collapse, right? Because with this massive star, we don't know any mechanism to stop the gravitational collapse. All right, that is the physical motivation of that's the physical motivation for the existence of black hole. Okay, before this, below this mass, we have, for example, the electron degeneracy as well as the neutron degeneracy to stop the collapse. All right, but then beyond this, yeah, we don't know any mechanism to stop the collapse, and hence we expect black hole to exist. Okay, and indeed we have detected black hole, where we have observed black hole, right, almost directly. Okay, now I'm back to this one. Okay, we have a star collapsing. All right, then since we don't know anything to stop the collapsing of the star, then at some point the star must have collapsed to a again a very small, very hot, very dense region. Okay, so same as the Big Bang, which means that we are going to need quantum gravity to properly describe this situation. Okay, so this is just a picture of the first image of a black hole. Okay, all right, and also when we talk about a black hole, there is also another problem that is known as the information paradox. All right, so according to classical GR, nothing can escape from a black hole, and hence a black hole can only increase in size. All right, but if we include, if we consider, if we use curved space-time quantum field theory, all right, in a black hole situation, we find that Hawking find that black hole actually radiate. Right? Black hole actually radiate thermally with this temperature, right? With this temperature. And interestingly, you see, in this expression of the temperature, we have all the interesting constants. We have h bar, which means that quantum physics is involved. Right? We have c, which means that special relativity is involved. We have capital G, which means that gravity is involved. And we also have kb, which is the Boltzmann constant, which means that thermodynamics is involved. So, so black hole evaporation is a very interesting. It is a very interesting arena for theoretical physics, because from this expression we have everything, right? We have everything. We have all constants over here. Okay. Okay, and then because black hole radiates, right? So that means that at some point the black hole might might be may just evaporate, right? And so far, if we only use quantum field theory in curved spacetime or just semi-classical gravity, it's unclear what's going to really happen towards the end of the black hole evaporation, right? And we expect that in order for us to properly describe what is happening at the end state, we need quantum gravity again. So this one is yet another motivation of 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 why we need quantum gravity. Okay, so I think I'm going to skip this part because I'm running out of time. Okay, so just to summarize, I can say that we have 4 motivations for needing quantum gravity. 1, unification. 2nd, quantum superposition. 3rd, early universe. 4th, black hole singularities, black hole evaporation. All right. Okay. So the need for a modified gravity theory has been recognized, in fact, by Einstein himself as early as 1916s, right? Because just after, at the end of his gravitational wave paper, he already pointed out that not only we have to modify Maxwell theory, Maxwell electrodynamics, but also this new theory of gravitation. Okay. Okay. Now I want to talk about the second part of I want to go to the second part of this talk, which is about the approaches to quantum gravity. All right. Now, in the broader sense, we can classify the various approaches to quantum gravity into 6 types, right? Into 6 types. By the way, when should I stop talking? Is it 3:30?
Doctor, your time is until 3:30. So
3:30. All right.
you may continue. Yeah.
All right. Okay. Thank you. Okay. Thank you. Okay. Now back to what I was saying just now. Okay. In the broader sense, we can classify the approaches to quantum gravity into 6 types. All right. So where the first one is the quantization of GR itself, which we can further split into 2 approach. Okay. The second one is general. It is what I would call as general relativization of quantum theory. Okay. The third one is we try to derive GR as the low energy limit of another quantum theory. All right. So for now, string theory is the only candidate for type 3. And then the fourth type is, well, both the GR and quantum theory are the limits of the low energy limits of some more fundamental theory. Right. So this one, I don't know any approach that I don't know any approach that is of this type. All right. And so this is not really a popular approach. Okay. And then so according to Isham, only included this first 4, and then I just add this another 2 at the last one. That is type 5, which is where we retain the classicality of gravity, but we use quantum method, right? So under this category, we have quantum field theory in curved spacetime as well as semi-classical gravity. Okay, and then type 6 is if we just analyze what are the phenomenon that could arise due to quantum gravity. All right, like for example, in quantum gravity, we expect that there will be a minimal length scale. Right, we expect that there will be a minimal length scale. That what we can do is that we can just try to introduce ad hocly into our theory a minimal length scale. All right, like for example, perhaps we can come up with a quantum field theory that has a minimal length scale, and then from there, we just find what are the consequences of that minimal length scale, even though we are not deriving from where that length scale comes from. Okay, so that's what is meant by phenomenology. Okay, now if we are to take the much narrower definition of quantum gravity, then I would say that only type 1 and type 3 qualify under that definition, right? Because if you remember, the narrow definition is that quantum gravity are attempts for us to study the quantum properties of gravity. All right. Now, in the second approach, we do not quantize gravity. All right. Instead, we general relativize quantum theory. Okay. So, in a sense, when we are talking about quantum gravity, it is as if quantum mechanics is superior, which is why we need to quantize gravity. Right. It is quantum mechanics that is influencing gravity. Okay. Whereas type 2 is about us taking gravity and make gravity to influence quantum theory. All right, because as I said just now, in our standard quantum theory, in our standard quantum mechanics, gravity doesn't come in. Okay. Okay. So for the remaining of the talk, I'm just going to talk a little bit about some of the approaches. All right. Okay, so this one is just showing you the timeline of quantum gravity research. This one I take from Ravelli, okay, where he outlined the history of quantum gravity. So I'm just showing here, right? Okay. Okay, so before I proceed, I just wanted to first try to highlight the difference between the so if you look at this, the first type, the quantization of GR, there are under this approach we can divide it into two approaches, right? One is known as the canonical approach, and the other is known as the covariant approach. Okay, so the only difference, the main difference, the difference between these two approaches is how we treat space-time, right? Is how we treat space-time. And for that, let me first remind you what is it that we learn from special relativity as well as GR. Now, according to special relativity, space and time are on equal footing, and we should view both space and time as a single entity, right? As a single entity, as space-time. Okay, and in particular, there is also no notion of absolute time, and hence there is no notion of simultaneous plane of everything occurring. All right. So this picture is showing our Galilean or Newtonian picture of the flow of time, right? Where at any given moment we can describe space at a given time, right? Space at a given time, independent of the motion of the observer. Okay. Now, when special relativity comes, it says that this is not the case. This is not true. All right. Instead, what we regard as simultaneous, what we regard as events that are happening simultaneously, depends on the state of motion. Depends on the state of motion of the observer. All right. So let's say, for example, according to this observer, that is just so in this diagram, time is moving upwards. All right, time is moving upwards, and space is in this direction. So in this right picture over here, we have an observer we have a set of observer that is not moving, right? Which means that they are just staying at the same place and they are just flowing through time, right? So according to them, this is their what we call as plane of simultaneity, right? These are planes that contains all the events that is happening at the same time. Okay. Whereas on the left hand side, it is showing the planes of simultaneity according to someone who is moving, right? So let's say this set of observer, they are moving to the left, all right? Then according to them, this, according to them, let's say at this time, at the second time over here, so these are the events that is happening at the same time, right? Which is clearly different from what the observers on the right perceive. Okay. Okay. Now the main point is that according to special relativity, we should treat space and time as a single entity, right? We should not. We should not. We should treat this. We should treat this. This description of flow of time carefully, right? Carefully. Okay, now comes to the difference between the covariant and the canonical approach. In the covariant approach, we really do view space-time as a four-dimensional entity throughout the process, throughout the quantization process, right? Whereas in the canonical approach, we do what we do over here, right? We do what we do over here. We in the canonical approach, we do split space-time into a collection of space that describes events that are happening at the same time, right? At the same time. So that is the main difference between the covariant and the canonical approach, right? Technically, this means that we restrict the topology into this kind of thing. So yeah, you can just ignore that one. Okay. Now, if I am to take this, if let's say if I am to take this cylinder as an example, the difference between the covariant approach and the canonical approach is that the covariant approach would treat this cylinder as a cylinder as a whole, right? Whereas the canonical approach is going to treat this cylinder as a collection of circles. Okay, so this is the difference between the canonical and the covariant approach. All right. Okay. All right. So now I wanted to describe a little bit about the about the different approaches. But then, in order for me to do so, I am going to use the term the metric. All right, which because the central quantity in general relativity is the space-time metric. All right. Okay. Any question? What? Okay. But then, in order for me to use that term, I think it would be best if I at least try to introduce what it means first. All right. So it is such you can introduce the metric in an intuitive way if we consider, for example, this map over here that we have. All right. So so this is the map of the world. All right. Now suppose that I wanted to ask you to ask you to give me what is the length, for example, between this point and this point, these 2 points. You just use another color. Okay, for example, this point and this point. All right. So clearly, you cannot simply take a ruler. All right. You cannot simply take a ruler and then just measure the distance between these 2 points, and then just say that that is the distance. Obviously, you cannot do that, right? In particular, if let's say I want to compare between the distance of these 2 points and these 2 points, right? I cannot say that the distance between these 2 points and the distance between these 2 points are the same. Okay. The reason is because this map is not a faithful representation when it comes to distances. Right? It is not a faithful representation of the distances. In fact, if we are to be more accurate, in this map over here, everything that is at the top has actually been enlarged. okay, has actually been enlarged. Okay, so what we need to do is that for each point on this map, we have to put a scale, right? We have to put a scale in order for us to convert this measurement on the map, perhaps 2 millimeters, right, to actual meters, right? We have to put some scale on this map, right? And the scale is going to vary across this map, all right? Like for example, perhaps this 2 millimeter over here is equivalent to, I don't know, I'm just going to quote, for example, 10 kilometers, all right? Whereas 2 millimeters here is equivalent to 1 kilometer, for example, right? So of course, the value is not correct, but you get the point, right? So the point is we have to put a scale at each point of this map, right? So that scale is what the metric is, right? So that scale is what the metric is, okay? So this one is what I okay. So suppose that we have, so what I mean over here is that suppose that we want to find a distance here, ds, right? That what we can do is that we can consider this distance dx dy, and then we can use Pythagoras theorem to find what ds is. Okay. Now, if the map is a faithful representation, then ds would just be given by this formula, all right, which we can write it in this second line here, right, in this way. Okay, so this metric over here in the middle is what the metric is, all right, what is the metric is, but this one is for flat space. Of course, this is not accurate, right? As I said just now, we need to put a scale at each point on the map, all right? So what that corresponds is that we replace this metric, this metric, which is the metric for the flat space, with the metric for a spherical surface, which I'm not going to give what is the form. That's not the important point, right? The important point is that we need to replace this part of the equation with what is known as the metric that encapsulate the physical distance. Okay, so that's the main point, and this is what is known as the metric. All right. Now, when it comes to space-time, if on the map over here, the metric is what encapsulates distances on the map, on the surface of the Earth, then the space-time metric is the quantity that give you what is the space-time distance. Okay, what is the space-time distance? That's the main point. Okay. Okay, now moving on. If we think about it carefully, right? So the surface of the Earth is not a perfect sphere, right? It is not a perfect sphere. Some places have hills and some places has valleys, right? Which means that if, let's say, for example, if I go back to here, if let's say I want to find the distance between this point and this point, right? If I really want to find what is the distance as measured on the surface of the Earth, right? I cannot simply assume that the Earth is just a flat space, right? I need to consider the fact that we have land over here and we have sea over here, which means that this point is higher than this point, right? So which means that even if we use the spherical metric, that's still not going to give us an accurate distance yet, right? So what we can do, on the other hand, we can add a certain deviation to get that information accurate, right? So instead of just using this spherical metric, we add this part over here, which is the metric the metric that encapsulate the deviation away from perfect sphere. Okay. Okay, why is it that I point out this one here? Because I want to talk about covariant quantum gravity. So in this approach, as I said, we still treat space-time as a four-dimensional entity. All right, but how is it different from? But then, how did they do it? What they do is that they split the metric, the full space-time metric, into two parts. Okay, one, the first part is the metric corresponding to flat space-time, which is a space-time without gravity, according to certain observers. So that there are some technical subtleties over here, but for now, let me just say it that way. We can split the metric into the part that describe a flat space-time, okay, and some deviation away from that flatness, right? From that flatness, okay. Yeah. Technically, this one is only suitable for weak gravity, okay. Okay, but then in order to obtain quantum gravity, what we do in this approach is that we only quantize this part. We only quantize this deviation, this h mu nu over here. Okay, this h mu nu. We only quantize this part, similar to how we quantize electromagnetic field. Right, similar to how we quantize electromagnetic field. And as a result, this gives rise to particles of gravity that we call as graviton. Right, similar to how when we quantize electromagnetic field, we get photon. We get the idea of photon. Okay, so similarly, in this way, when we quantize just this part, we get graviton. Okay, so the main characteristic of graviton is that it is massless and it has spin 2. Okay, it is massless and it has spin 2. Okay, all right. So that is the main point about this approach. However, the obstacle for this approach is that this theory is not renormalizable, right? Now, similar to quantum electrodynamics, which is the quantum version of electromagnetism, whenever we do integrals in this approach, we are going to find that a number of integrals are just infinity, right? Taken naively, the integrals are just infinity, right? But then there are a certain procedure that is called renormalization that we can do in order to absorb this infinity into physical parameter. All right. Okay, so that we can do in QED. However, in this covariant approach, this is not possible, unfortunately. So we cannot absorb away this divergent integral, right? And that is the main problem for this covariant approach. Okay, that is the main problem for this covariant approach. And until now we don't know how to deal with this infinity. All right. If we stop over here, right? Of course, after that there are attempts. For example, to include supersymmetry, which gives rise to supergravity. Okay, which means that what this does is essentially it introduces another partner particles, right? So just now we have gravity, which is a massless spin 2 particle, which is a boson. When you include what's known as supersymmetry, we introduce another particle, another partner particle known as gravitino, which is a fermion, and it has a half integer spin. Okay, but then if we apply supersymmetry to the standard model, this implies that for each particle in the standard model, the 61 particles, for each of them we have a partner particles, right, which are of the opposite nature in some sense, right? But then so far we have not found any of these partner particles, and that's the problem with supersymmetry, right? The problem is that so far we do not find any of these supersymmetric particles. Okay, so yeah, so that's the main problem for this part. Okay, so I think so from here I think I'm going to go on to string theory, right? So string theory, it is originally an attempt to describe strong nuclear force. nuclear force. So string theory is not originally unified. It's not originally meant to be a theory of everything. No, right? So string theory originally is an attempt to describe strong nuclear force, but then nowadays it has been replaced by quantum chromodynamics for strong force, right? So we don't use string theory to describe strong force anymore. And the main premise of string theory is that instead of particles, the fundamental entity are strings. All right, and after that we generalize it to branes, etc. But the point is, the historical point is that the main fundamental entities are not point particles. Instead, they are strings. Okay, so what is the main point over here? The main point is that it turns out some of the strings, right, can vibrate in a particular way that we can identify it as a massless spin 2 particles. So just now I mentioned that is the characteristic of graviton. All right, and so because of this, it has been suggested that perhaps we can describe quantum gravity using string theory. So that is how string theory becomes a candidate for quantum gravity theory. And because it can also, in principle, describe every other particles, it is also a candidate for a theory of everything, right? Okay. However, the main problem, I think, with string theory is that in order for it to work, we have to have more than 3 + 1 dimension. Yeah, we have to have 9 dimension, at least in one version. We have to have at least 9 space-time dimension and 1 time dimension. But so far, we have not detected any extra dimension yet. All right, so that's the main problem. So this is meant to illustrate how the extra dimensions might actually be a small dimension, like in this diagram over here. So from afar, we see this as a single line, right? But then if we zoom in, we find that there is another dimension that form a circle, all right? That we say that this dimension is a small dimension. Okay, so this is just to illustrate small dimension. Okay, I just want to point out here that there are actually not one string theory. There are 5 string theory. All right. So yeah, and in 1995, Edward Witten proposed that all of these 5 string theory, they are limits of another more fundamental theory, which he called as the M theory. All right, all of which has a low energy limit as a 11-dimensional supergravity. Okay, so this is about string theory. All right, so I am running out of time, so I'm just going to rush through a little bit about the canonical approach. So as I said, the main difference with the covariant approaches now is that in the canonical approach, okay, we start by foliating the 4-dimensional spacetime into a collection of 3-dimensional space. All right, we start by doing that, and on each of that 3-dimensional space, we have its own metric. Right, it has its own metric. Okay. Now, why is it that I highlight this part? Because, so let me just skip this part, because I want you to recall, in order for us to describe a freely moving particle, right, we start by considering a classical particle, and we can describe it using its position as well as its momentum. Okay. Now, in order for us to proceed with the quantization, what we do is that we promote both of these variables to become operators, right? To become operators, satisfying this commutation relation. And then from these operators, we can introduce the wave function, which obey this Schrodinger equation. Okay. Now, what I wanted to highlight is that in the canonical approach, we do something similar, right? We do something similar. We're using the metric of each of that three-dimensional space just now. Okay, that QAB just now, and its corresponding what we call as conjugate momentum. Okay, we quantize it by promoting them to become operators. All right, and then we can then introduce the wave functional of that space. All right. So if the wave function gives us if the wave function for a particle gives us the probability of the particle being at a particular place, then this wave functional give us the probability for some particular metric to be realized in the real world. Right. So that is what this wave functional means. In other words, this wave functional is the wave functional of the universe. So it is the wave functional of the space-time of the universe itself. And the corresponding Schrödinger equation is what is known as the Wheeler-DeWitt equation in this case over here. Yeah, I'm not going to go through the details here. But what to highlight is that we don't know how to solve this equation, right? Because this equation has several technical difficulties, right? And even if we manage to solve it, it's not yet to the point where we can apply significantly to our universe. Okay. Now, canonical gravity is the prerequisite to loop quantum gravity. How? Simply by a different choice of configuration variables, different choice of variable for us to quantize. Just now, in the original canonical gravity, we use the metric itself, right? We use the metric itself and its corresponding momentum. Okay. In loop quantum gravity, we use, well, to keep things short, I'm just going to say that we use a different type of variable, right? We use a different variable, including a variable that can be associated to loops in space, literal loops in space, right? And that is where loop quantum gravity, the term loop quantum gravity comes in, right? Because the variables that are being used in loop quantum gravity are associated to loops in space, Yeah, so the main highlight that I wanted to say about loop quantum gravity is that from quantum gravity, we do get a result that says that both the area and the volume are quantized, similar to how energy are quantized, which means that volume and area can only take a certain value. There are values that it is simply impossible for us to have that area or that volume. Okay. Right. So loop quantum cosmology is just we apply loop quantum gravity principles to cosmology, and the main result is that the Big Bang doesn't exist in this loop quantum cosmology. We have the Big Bounce instead of the Big Bang. Okay. This is called a set, so I am running out of time, so I think I'm going to skip this one. So this one is just listing some of the possible implications as either as a consequence or predictions or postulates of the different approaches to quantum gravity, right? So just now, and these are often used in type 6 approach, which is phenomenology just now. All right. Okay, yeah. Okay. Just to close my talk, I just wanted to highlight that if you are to ask about what are the challenges to quantum gravity, I think I can summarize it in this four main problems. One is the conceptual problems, because some of the concepts used in gravity is not have a different status than what is used in quantum theory. right? Like for example, like for example, in classical GR, everything is definite, whereas in quantum mechanics, things are probabilistic. All right, so we have conceptual clash there, right? We also have technical challenges in the sense that we have equations that we don't know how to solve. Okay, and then experimental, I've said it just now. We are not yet at the scale where we are able to probe quantum gravity directly. And lastly, I would also say the economy as well, because if we are to build a larger collider, that would be even more expensive. Perhaps that money could be used for something better, something more beneficial, right? So I think that's all. I wanted to stop there. So this I put some references of the books as well as the articles that you can start if you are to read more about quantum gravity. And this and I also include here the Stanford Encyclopedia of Philosophy as well as Wikipedia, where you can just use as a really just a starting point. All right, you're not going to get much technical details there, but you can start there. Okay, so with that, I end my talk. So thank you.
Thank you, Dr. Husni, for shedding light on quantum gravity. We will now start the Q&A session. For all the participants in YouTube and WebEx, please type your questions into the chat box. For those in YouTube, we'll be compiling the questions that you type in the chat box for Dr. Husni to go through. However, for now, let's go through the questions from WebEx first. So the first question would be from Lo Kai Xuan. He says that I want to ask, is the gravitational field strength or other field strength is just the intensity that we define as power per area?
Yes, I didn't quite get the one.
Okay.
Yeah, I would say that it's a yes. Yeah. Well, gravitational field strength. But for each field, you can define the strength using the field itself. Yeah, but you would end up with intensity as a power per area. Yeah.
All right. Thank you, Dr. Husni. For the second question would be from Izat. Wouldn't the issue of superposition of space-time be solved by simply dismissing Copenhagen's interpretation as false?
Well, we could do that, but then even if we use any other interpretation, I suspect that we would still have trouble in describing what actually happening. All right, because even if you use the manual, yeah, we still don't know how to describe the situation mathematically, at least.
Is that all, Dr. Husni?
That sounds the same.
All right. So the third question would be from Mohamad F. Umar. So he asked, so loop quantum gravity is type 1 approach.
Yes, yeah. Loop quantum gravity is type 1 approach. More specifically, it is the canonical approach, canonical type 1 approach. Spin foam, on the other hand, is a covariant type 1 approach.
Following that would be from Logesh Kumar. Besides LHC energy limitation to probe quantum gravity, why the Planck scale is a limitation for us here? Is it because our current maths collapse here and a new physics is needed to deal with Planck scale limitations?
Is it because our current mass collapsed here? Oh, yeah. So of course, the main problem is that the main problem is that we do not have direct access to that Planck scale. That is the main problem, right? And secondly, some of the and secondly, it has also to do with the technical challenges in getting the calculations done. So yeah, so I guess that is correct what you said. Yeah.
Follow up to that question would be, would developing the math be able to deal with this Planck limit possible to open a bigger door to make quantum gravity framework?
Okay. I think let me answer in this way. So as I said just now, so one of the main challenges is the fact that we are not able to directly probe quantum gravity with experiments, right? And so the focus nowadays, the focus in the theoretical physics community is primarily trying to come up with a consistent mathematical framework. All right. We can do that, but then eventually if we are to describe the real world, we still need to come up with predictions that uh, are predictions that we can test, right? Perhaps even not directly, perhaps even indirectly. Like for example, some quantum gravity theories predicts that the equivalence principle would eventually be violated at some scale. So perhaps if we can find these violations of well accepted principles, that will also be an indirect indirect uh, indirect verification of quantum gravity theory. And also hopefully each quantum gravity theory will provide a slightly different prediction and not just the same prediction that experiments cannot distinguish. So yeah, so eventually we still need experiments if we are to describe the real world. Otherwise, it's just gonna be just consistent mathematics.
Thank you, Dr. Husni, for that answer. So another question from Dr. Rabi Omar would be, could you explain why the space-time curves in the presence of mass? He says that, I know it is the Einstein equation that produces the space-time solution, but why does it curve?
Oh, okay. 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 So this question, so GR doesn't say anything about why energy curves space-time. It simply says that it does. So why does it curve? I don't know.
Is that all, Dr. Husni, for the answer?
Yeah, that's all. Yeah.
Okay. So next would be from Thomas Yeo. Would you mind explaining a little about what spin foams are?
Oh, spin foams. Okay. So just now, when I was talking about loop quantum gravity, right? So notice that loop quantum gravity arises in the context of canonical approach. All right. So the states of loop quantum gravity, which I state as spin network just now, all right, that only describes what is the situation of space. What is the it can only describe quantization of space, not yet space-time. Okay, which is why in loop quantum gravity we have the quantization of area, quantization of volume, but we don't have yet quantization of time in the sense of the minimal amount of time. All right, and that's where spin form. And in order for us to do that, we need to complete the process of quantization in loop quantum gravity to include what is known as to include what is known as the Hamiltonian constraint. in order to describe the evolution of those spin network states, of those loop states. Spin form, on the other hand, start directly with a four-dimensional spacetime, and quantize it in a in an approach that is closely related to loop quantum gravity. So I think that's all that I want to say for now for loop quantum for spin form.
There's another question about what is big bounce from Lai Jianhao.
Okay, the big bounce. Okay, okay. To talk about big bounce, let's first recall the Big Bang, right? According to the Big Bang, right? If we reverse the time, okay, so there will come a time where everything becomes where everything in the universe uh, is in a very small dense region. All right. Well, mathematically that point is mathematically that point has a zero volume, not just small. It has zero volume, which is why that point is a singularity. Okay. And according to the Big Bang, there is nothing before that. So that point of Big Bang is the literal starting point of the whole universe. Okay. Meanwhile, the Big Bang, the Big Bounce, what the Big Bounce said is that if you reverse time, the universe will come down to a very small volume, but finite. Okay, but finite. And before that point, before the universe reaching that minimal volume point, all right, we have a universe that is contracting, which means that in the Big Bounce theory, we have a universe that is contracting, all right, contracting to that very small region. Okay, that small region then expand again to become our universe. So that is the Big Bounce. Yeah.
There's another question. What is the specific features that distinguish loop quantum gravity as a type 1 approach?
So the main point is that type 1 approach is where we take GR and then we apply quantum principles to it. All right. And loop quantum gravity is precisely that. We start from GR and then we apply quantization principles to GR. That's it.
Okay. There's another question from Li Bingyi. Doctor, our main approach now is to unify quantum and GR under the assumption that they are able to do so. Could it be possible that how gravity works could be completely different than the rest of the forces, and quantum effects won't happen even in the Planck scale?
If you ask whether that is possible or not, I would say that is yes. But still, you have to find ways to describe the discrepancy. And I suppose what you're asking is that is it possible that uh, is it possible, for example, if gravity is a truly classical field, right? Is that the question? I think. Oh yeah, so yeah. So from the wording, I think when you say quantum effects won't happen even at the Planck scale, I assume that you are referring to quantum effects of gravity. All right, which means that you are asking, is it possible that gravity is a truly classical is it possible that gravity is a truly classical field? Yes, it is possible, and that is what type 2 approach is about, which is gravitization of quantum theory.
The Li
Yeah,
Bingyi
type 3.
adds on that could it be possible that it's not classical nor quantum?
Yes, possible. That is where type 4 comes in. Yeah, that's where type 4 comes in. But then so far, no one really pursue that approach. Yeah. Causal set theory, maybe a little bit, but still not quite type 4. Yeah.
Okay, thank you, Doctor. There's another question from Kevin. Uh, Hi, Doctor. I'm curious, what are the starting points for the general relativization of quantum theory?
We take quantum theory and then we add gravity into it. That's it. Yeah. Maybe
All right. Uh,
maybe we change um maybe we change Schrodinger equation to another, I don't know, Schrodinger something equation that is in the Schrodinger equation, you modify it to include a gravitational term, for example. So that would general relativize quantum mechanics. Yeah, quantum mechanics.
so, Doctor, this will be the last question. So it's from our first participant who gave the first question. How time dilation and length contraction is related to quantum gravity?
I don't think this is often discussed because time dilation and length contraction, those are concepts in special relativity. So I suppose the assumption would be that, I mean, the first thing is that what is the notion of time what is the notion of time and length to begin with in quantum gravity, right? Because once you go into quantum gravity, even the very notion of time interval and length is something that you have to make sense of. There is a question of, even does time even exist in quantum gravity? Yeah, what is time in quantum gravity? Because quantum gravity is about the quantization of time and length itself. But in any case, we would suspect that any quantum gravity theory must be able to eventually reproduce GR as well as special relativity, of course, in appropriate limits. So yeah, so as to that question, I don't recall this notion, this concept is discussed in quantum gravity. Yeah, that's all.
Okay, thank you, Dr. Husni. As there are no questions in our YouTube participants, we will now end the sharing session. But before we end, I would like to invite everyone to please turn on your video camera first, because we will be having a photography session now. Ms. Fatnin, can you take charge for the photography session?
Okay, I will start taking the picture. You guys can open your camera. Okay, 1, 2, 3. Okay, wait, one more. Okay, one more. 1, 2, 3. Okay, done.
Thank you, Ms. Fatnin, for your help. Now, after the photo taking session, we have now officially ended our sharing session. Thank you so much, Dr. Husni. And thank you everyone for your cooperation. We will now release the MyCST form, which we will close after 10 minutes. Kindly fill in by then. Once again, thank you very much, Dr. Husni, for sharing your great insights in the field of quantum gravity. Hopefully, we'll see everyone again in our next coffee talk. Thanks, everyone.
All right. Thank you, everyone.
Thank you, Doctor.
you.